Imagine a world where you discovered a chemistry that could take the water that's in our air and turn it into drinkable liquid water. You could provide people who have limited access to water to be able to comfortably cool off, have reliable plumbing, wash their clothes, stay hydrated. You'd probably save lives, maybe even win a Nobel Prize. That's exactly what happened with these three chemists, Richard Robson, Susumu Kitagawa, and Omar Yaghi, who just won the 2025 Nobel Prize in Chemistry for their research in metal organic frameworks, also known as MOFs. So today we're going to break down why MOFs are so incredible, specifically at capturing molecules like water, and why there's no doubt in my mind that this deserves a Nobel Prize. If you've never met me, welcome. Thank you for stopping by. My name's Matty C. I usually make videos on different types of engineering in the pharmaceutical and drug discovery world, but metal organic frameworks have a very special place in my heart, mostly because of this man, Omar Yaghi, who I actually had the chance to meet way back in my early PhD days. He was a super sweet guy who was really able to connect with the grad students and show that trials and tribulations usually lead to great chemistry. Chemistry that now has a Nobel Prize. To best understand MOFs, we really have to go back and start with their origin story, which for the sake of today starts in the late 1980s. Here's where we meet Professor Richard Robson, the inventor of the first ever metal organic framework. Professor Robson always researched something called coordination chemistry, or taking simpler molecules and arranging them and combining them into these more complex 3D structures. Here's a high-level example. In the case of MOFs, metal ions, or clusters of ions, form these little nodes, and they're bridged together by organic linkers. A few of these linking events aren't super special, but as they continue to link together, they form these crystalline porous networks, very rigid, defined shapes that have many holes or pores within them. And you might think that holes are only interesting when it's Shia LaBeouf's 2003 classic, but this engineered emptiness is the most important part of a MOF. We'll talk more about surface area and how that can be applied to real-life scenarios, but for now, think of it as a molecular jungle gym with very precisely controlled spaces and add-ons. The more that we can control these spaces and add-ons, slides, swings, whatever it may be, the more ways we can play with our pals. Now, getting a little more complex, here's the actual chemical structure of one of Dr. Robson's first MOFs. These purple dots are copper ions, and they are linked together through these cyclic organic structures. One of these linkages is called a secondary building unit, or SBU. It just has this pyramid-like shape, but it doesn't really do anything. But stack a few of these SBUs together, and that's where you get that final crystalline structure that have these large pores, or these large cavities. Now here's where the engineering gets interesting. These pores let you control molecular movement. Different molecules, represented here by different colors and sizes, can move through MOF pores at different speeds. That speed is dependent on how many intermolecular interactions happen between those molecules. The more interactions, the slower they move. Decrease pore size, larger molecules can't fit through. Make the metal clusters positively charged, well, negatively charged molecules get attracted and slow down. And you can tune these interactions strong enough to permanently trap molecules within this metal organic framework. It's like if you could customize your jungle gym to have the right number of slides and swings to optimize which friends you want in on the fun. If you know Bingo the Bully is afraid of heights, time to add a 40-foot slide. These pores provide MOFs with an incredibly high surface area. On average, 1 gram of MOF has the same surface area as a football field. So if you think back to our water example, think of how much water we can harness with just a little bit of MOF. But more on that later. This discovery alone wasn't enough for Richard Robson to win the Nobel Prize because he didn't really apply it to real-world scenarios. It was really just lab-related things, like selectively entrapping acetone and other organic solvents. But it was enough to inspire the next generation of chemists through a few different ways. He showed that the tunability of these pores could control molecular diffusion much better than naturally porous materials that weren't tunable at all. He also challenged the next generation of researchers to expand on these principles and make more cool MOFs, saying that one day they could be modified to catalyze reactions, just like the enzymes in our bodies. And here's where we get to introduce our other 2 Nobel Prize winners, Omar Yaghi and Susumu Kitagawa. They were heavily inspired by Professor Robson's research, and over the next decade, we're going back and forth making different MOF structures, making incremental advancements. But in 1999, Omar Yaghi made a MOF structure that blew the doors wide open. Meet MOF 5, named after the number of stars that the chemistry community was giving it. You'll notice that the building unit on the left contains zinc, carbon, and oxygen. But like with all MOFs, what matters most is how those atoms are arranged. By linking zinc oxide clusters with a short, flat molecule like benzene dicarboxylate, they made a crystalline cubic lattice, which is shown on the right. It is incredibly rigid and incredibly stable. For the first time ever, Omar Yaghi's group made a MOF with permanent porosity. No changes in pore size regardless of how many gas molecules would interact with them. MOF5 was also stable up to 300 degrees Celsius and had a surface area of 2,900 square meters per gram. For context, this was around 10 times more surface area than naturally porous standards used at the time, which means MOF5 could bind orders of magnitude more than previous MOF designs. If Robson's original MOFs were a wooden jungle gym that gave you splinters and nearly collapsed at the slightest gust of wind, MOF5 was reinforced steel that could support all the homies. Robson made the structure that got people interested, but Yaghi made the structure that got people going.
No one knows what it means, but it's provocative. It gets the people going.
The physical properties and permanent porosity of MOF5 made it the gold standard within the MOF community. But let's not forget about Professor Kitagawa because his contributions are essential to the real-world applications that we see MOFs used in today. Professor Kitagawa took the opposite approach. Rather than replicate the stability and rigidity of MOF5, he postulated that flexible MOFs with molecules entrapped could respond to external stimuli, apply light, heat, pressure, and the MOF becomes flexible enough to release captured molecules. Remove the stimulus, and the MOF returns to its rigid form, ready to capture again. It'd be like replacing the boring solid floor of your jungle gym with a rope bridge. Whoa, look at how wacky and zany and fun this is, my friends. So stupid. So stupid. This stimulus-responsive behavior opened up a world of possibilities. Adaptive gas storage, smart sensors, maybe a device that could capture gaseous water and make it liquid. Whoa, 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 whoa. Slow down there, cowboy. Almost there. Just gotta wait a little bit longer. At this point, Professor Kitagawa was very similar to Dr. Robson, where these discoveries were amazing, but they were mostly kept to the lab scale. No real applications yet. The problem is that at this point, they still didn't know enough about MOFs. Now, this is where Omar Yaghi comes back into the frame to make his next big contribution. A contribution that most experts agree is the reason why they won the Nobel Prize. In order to make the next generation of metal organic frameworks, Omar Yaghi wanted to design so many that he could predict the structure of that MOF before it was even made. He developed a system known as Reticular Chemistry. The idea is simple. Take the same building block, the same SBU, and change one component at a time. Here, for example, he took MOF5's zinc oxide structure and systematically increased the length of that organic linker, which then expanded the pore size. Increasing the pore diameter from 2 to 10 nanometers drastically changes how much of a particular molecule he could capture, and in some cases, what molecules he could capture. It's the difference between monkey bars spaced 1 foot apart versus 5 feet apart. The spacing fundamentally changes whether or not Matty C could swing his fat ass from one end to the other. Now scale this up. Swap zinc for copper, add aliphatic side chains to that organic linker, adjust the coordination chemistry from a tetrahedral to an octahedral. Each variable changes MOF structure. And as we see all the time in chemistry, structure predicts function. So Omar Yaghi's group made such a vast library of MOF architectures that they were able to predict the final MOF structure and thus its molecular binding function just by knowing its metal organic components. Now, in the age of AI, I feel like we see this a lot more. It might seem a lot less exceptional to just make big data sets and libraries of things, but in the late 1900s and early 2000s, this systematic approach was a complete 180 of what most chemists were doing, which was just trial and error. Make one MOF, define it, see if it can do anything. If it wasn't good enough, you try again, leading to literally thousands of different MOF structures with well-defined characteristics. If it's still not clear why this reticular chemistry is so Nobel Prize worthy, let's dive a little deeper. Here are just a few examples that Omar Yaghi's reticular chemistry has inspired, most of which were actually done by other researchers. You notice that some are flat and stackable. Others are spherical. Some have inherently large pores, like MIL 101. Others have small pores, like CAF 20. And remember, structure predicts function. The large pores of MIL 101, for example, are spacious enough to fit molecules that can catalyze reactions, whereas the small pores of CAF 20, combined with their exceptional stability in water, makes them an ideal candidate for capturing CO2. Companies deploy CAF 20 at scale to minimize greenhouse gases that are released during their industrial processes, thus limiting climate change impacts. Let's look at another example. Hexagonal clusters of Nu 1501 provides some of the highest total surface area of any MOF family, allowing it to capture high amounts of hydrogen gas at low pressure. This is being used to finally make an efficient, non-explosive hydrogen engine, something that researchers have pursued as a clean fuel source for decades. But you'll want to focus on MOF 303 because it is finally time to talk about the MOF structure that's able to make liquid water out of thin air. MOF 303's aluminum nodes have been modified to have specific binding sites that hydrogen bond with the water vapor in the air. Now, remember how Kitagawa wanted dynamic MOFs, ones that respond to different stimuli like temperature? Well, MOF 303 is one of them. At lower temperatures, the structure is rigid, and it's able to bind to water tightly. But at higher temperatures, it becomes more flexible and temporarily deforms, thus releasing the water vapor. And it spits out that vapor onto a solid support that's cold enough to condense the gaseous water into something that's liquid. So in a 24-hour day, it binds the vapor when the sun is down and it's relatively cold, and then releases it when the sun is up and it's relatively hot. And this isn't just a theory. Omar Yaghi's company, Atoko, is putting kilograms of MOF 303 and cold solid supports into this capture device, and then placing it in different cities all over the world. And though it depends on the average humidity of that city, they've been able to capture up to 90 liters of water per kilogram of MOF per day. For context, that's enough for the average Canadian to comfortably drink, shower, and cook for an entire day, or about half of what the average Canadian teenager would need. And if you're thinking, wow, that sounds amazing, but you probably need really humid climates to make this work, then you'd look like a dumb idiot. Omar Yaghi and his team were able to pull 7 liters of water per kilogram of MOF per day in the Mojave Desert, a literal desert with 10% humidity. Like, that is unbelievable. How do you even do that? That's like 5 Jim Bro water bottles. Think of how far that would go for people who have basically zero access to fresh water. Obviously, I'm convinced. I think it's an amazing technology, but no matter how amazing it is, there will always be some limitations. And cost is usually the biggest one for any groundbreaking scientific technologies. Typically, MOFs go for $10 to $70 per kilogram, which is more than double the industry standard for comparable porous materials, such as zeolites or activated carbon. And this cost stems from complex synthesis requirements, which need very controlled atmospheric conditions, precise temperature regulations, and many different steps to purify them. So when you're scaling that to an industrial level, those costs really compound quickly, especially since the goal of this technology is to produce water for an entire village. My personal concerns are around people trying to use them for biomedical applications. You'll see more and more researchers trying to use MOFs for drug delivery and pathogen filtration. But in my opinion, the toxicity data doesn't look fantastic. It's not super convincing. I think there still needs to be a lot more work into monitoring immune responses and the biodegradation to make sure that they don't stay in your body forever. And hey, I love research, so I hope people keep researching it to try and prove me wrong. But a large part of me thinks that because we already know MOFs are great at these environmental applications and water harnessing applications, why diverge before we've hit the peak of what those applications can use MOFs for? You know, think of how amazing it would be if in our lifetime we were able to provide every single human with access to fresh, clean water, or being able to capture enough greenhouse gases so that we can hit those global targets without having to compromise for other aspects of our lifestyle. I'm looking at you, paper straws. I'm choosing to stay hopeful. We're gonna get there in our lifetime. I believe it. So it'll happen. So thank you, Professors Robson, Kitagawa, and Yaghi, and everyone else in the field of metal organic frameworks for your incredibly important discoveries. You're changing the world one jungle gym at a time. Equally as important, thank you all for stopping by, and we'll see you later, nerds.